Well, hello and welcome. In this video, I'll be working through all of the solutions for our Chapter 7 test review. So without further ado, let's go ahead and jump on in. First couple of questions on this review are just evaluating functions at specific points or ordered triples. So in this case, notice this is a function of x and y, and just wants us to essentially plug those values into their corresponding spots. So as it's defined here, as you can see, it's x is first, y is second. So for part A, I'm going to be plugging in a 1 everywhere x is and a -5 everywhere a y is. So let's go ahead and just do that step. I've got 9, take away 4 times the x value being squared minus, and then the y value being squared. So now I just simplify using order of operations, start with our exponents, then do our products, then we do our addition and subtraction. So 9 is just going to hang out for a second, minus 1 squared is 1, times 4 stays 4, and then -5 squared, that's 25. Keep the subtraction, so minus 25. So now I just combine things as best as possible, or at this point just do all of the adding and subtracting. A couple of different ways we could do it. We could go just left to right, or combine our positives together, our negatives together, and that sort of thing. But regardless here, I think we can all do this mental math. We'd end up with 9 take away 4 is 5, take away 25, that would take me down to a value of -20. So this function's value at the point 1, -5 would be -20. Second one, this one just has a slight change to it. I'm actually going to plug in a variable for one of the numbers, but it doesn't really matter. It doesn't really change a whole lot of the approach. It's just my answer is likely going to contain t unless somehow, some way, it was able to zero out somewhere. But we'll just start the same way, plug in those two values where I see they need to go. So I've got 9 take away 4 times the x value of 2, square that, minus the y value of t, and square that. So now we'll simplify each one of these. 9 can't combine with anything yet. 2 squared would be 4, times 4 would be 16, so take away 16. And then t squared, there's not really much I can do with that. So now combine whatever we got here. 9 take away 16, that would be a -7 minus t squared, and since they can't combine, that's as good as it's going to get. For this second one, notice the only thing that's different now is now it's a function of 3 variables instead of only 2, but approach-wise still is pretty much the exact same thing. So we're just going to start with plugging in the numbers in their correct spots. This has been defined to be x first, y in the middle, and z as the third value. So plug those values in. I've got a big square root as my outer function here, so I will have to maybe simplify that when it's all said and done. That's going to be kind of more the last thing I deal with. So just remember to include it, don't drop it somehow, some way. Now we'll just plug in the numbers, so I've got 5 being squared, minus the y value, which is -4, and then add with the z value, which was 7. So now simplifying the inside, 5 squared would give me 25, minus a -4, which is really to addition with 4, and then 7 is still there as well. So it looks like, what do I got? 29 plus 7 more, that would be 36. And if I go ahead and simplify that, that turns into just a value of 6. If that wouldn't have been a perfect square, then we would have maybe looked to see if we could simplify, but that one was kind of nice with it being a perfect square. Similar to the first example, though, with letter B, this now has a variable that's going to go in place of a variable, so I'm expecting my answer to just be an expression, not so much a value, that likely contains the value t. So we'll just go ahead and plug in just like we did for part A. Got our big square root symbol, plug in 2 where x is, so this would be 2 squared first, minus our t, which was the y, and then z is a 5, so we'll just simplify whatever we can. Looks like I can do 4 plus 5 eventually, and get 9, and then the t was really just kind of along for the ride. So square root of 9 minus t is as good as that one can be written. Moving on now to questions 3 and 4, which generally have the same instructions. We're just dealing with 2 different kinds of functions. So each of these, what we're going to be looking for the domain portion of the question is just some functions maybe from our past that we know have restrictions. So things that we're not basically mathematically allowed to do. So things like dividing by 0 will be something to keep an eye out for. Taking or if you have an even root, knowing that we can't be a negative number on the inside of that. So like square roots, fourth roots, and sixth roots, for example, would be things to keep an eye out for. Or logarithms. I know we can't have negatives or even zero with logarithms when it comes to at least evaluating. So here, as we can see, we've got that more even root situation. I have the square root, so this is more, let's make sure that what's inside, so these are the 100 minus 4x squared minus 25y squared. Let's just make sure that that's not a negative number. And the easiest way to do that would be to just say as long as it's 0 or above, or greater than or equal to 0, in other words, that should be values that I'm allowed to be for this specific function. So now our goal turns into how could I make this look familiar and actually describe what that region would look like on the xy coordinate plane. So here, with powers of 2 on both x and y, that tells me it's more than likely a conic. Conics including parabolas, circles, ellipses, and hyperbolas as like the main 4 ones that we've hopefully encountered in prior classes. This one seems like, since they both have negatives, it's probably going to be more of a circle or an ellipse. With there being 2 different coefficients, more than likely this is going to be one that's an ellipse. So I'm just going to try and get it into a familiar format that I can maybe describe that ellipse a little bit better. Or at least if I needed to sketch a picture of what it would look like on that xy coordinate plane, I could. So I'm just going to add those 2 terms over, because generally with conics, it's best to have the x squareds and y squareds at least on the same side, leaving constants generally on the other. So adding the 4x squared over would make it positive 4x squared. Adding the 25y squared over gives me a positive 25y squared. And again, because those are different coefficients, definitely means it's not a circle. So since it's not a circle, I don't really want to have this number over here. I actually want it to be a 1. So I'm going to divide everything by that number to force the 1 to happen. Is less than or equal to, and now just reduce each of these and see if I could describe what this region would look like. So this would be x squared over, since 4 and 100 share 4, I'd have 25 left on the bottom. And then the next one, 25y squared over 100, 25 goes in both those numbers, so y squared on top, and then 4 on the bottom. So this is definitely an ellipse that has, it looks like the larger numbers under the x, so it's going to be longer horizontally. With an a value of the square root of 25, so 5, and then a b value of the square root of 4, so 2. So this would be something, if I needed to sketch it, it would be longer horizontally, where from center out, that would be a distance 5, and then center up or down, that would be a distance 2, if I needed to actually draw it. Because there's no parentheses, this would be 0, 0 as the center. So we could use all of that to our advantage, but as far as just like being able to test, like, is this all of the parts that are inside or outside of that ellipse, we could just test with any random point. I like using just the center itself. So if I plug in 0, 0, I get 0 plus 0 on the right side. 1 is definitely larger than that, so the shaded region, if I were to sketch it, would be everything shaded inside of the ellipse. So how do I describe now the domain? Well, I'm going to do that off to the side here. My domain would be the set of all points. I'll go ahead and describe the format of these points. The set of all points x comma y that are either on, because of the or equal to, so it could be on the ellipse itself, or since the shaded region would be inside, we also need to include any and all points that would be inside of the ellipse. And then I'll just write it in an equation format. 1 is equal to x squared over 25 plus y squared over 4. We could also describe it as an ellipse with a center at the origin with an a value of 5 and a b value of 2, but I don't think any reason for describing it that much in depth is a really necessary thing. So here, just at least identifying that we recognize it's an ellipse, it's everything inside or at least on it, some statement that accomplishes that feat. The range, on the other hand, now I just need to think of what is possible as an output. So this is now with square root as like kind of that big main function here. I just need to think what are the options with that square root. So the smallest number I can really be on the inside is 0. In fact, anything that would fall on the ellipse itself would give us 0. So here, if that's the case, I know it's going to be the smallest value is including 0. the maximum value, that is a little bit tougher to think about, but this is where you can just use a little intuition. If I square numbers, for sure those would stay positive. And so it would be 100, take away a number, potentially take away another number, potentially. So really, the only thing I could do is the largest value I could get on the inside is in fact this 100, because the only other option is if I had a value for x and y, is it would become something smaller than 100. So now let's just think, well, if I had somehow only subtracted 0 from 100, that would stay, and the square root of 100 would actually give me 10. So this could be as large as 10 as an output when it's all said and done. So my range is just any number that could fall between 0 and 10, so long as I'm satisfying a point that fits inside of what I just described the domain to be. As mentioned before, number 4 is basically the same instruction, so don't really need to describe everything a second time. The issue with this one, notice, is our outer function now is a log. So this is going to have a very similar approach of, okay, so there is a restriction. Whatever's inside of that log is going to be something that we're going to need to deal with. And with logs, it's basically, I just need to make sure that I'm positive. So the way I make sure I'm positive is just saying as long as I'm above 0, it's all good. So notice the big difference here really is just I don't have the or equal to anymore. So similar though from the last one, I see powers of 2 on both x and y, so this is more than likely a conic. So let's just move those over and see if we can recognize this a little bit easier. So I've got 16 by itself is greater than, and then that would be a positive x squared if I added that over, a positive y squared if that added over. This time the coefficients do match in front, they both happen to be 1, so this is actually a circle. So my domain for this one, again, we can do a quick double check just by testing the actual center of it, which would be 0, 0. 16 definitely is greater than 0 plus 0, so that would be true. So the shading of this, if I were to graph it, would be shaded inside of the circle. So the domain for this is basically the set of all points x, y again. Such that, or that make sure we satisfy being inside. So the set of all points x comma y that are inside the circle x squared plus y squared equals 16. So again, notice when we're stating what whatever the ellipse or circle or hyperbola, whatever it is, we're just going to essentially describe it using the equation of it, even though technically the inequality is the kind of the satisfying part. So we're saying by including all of the points inside, that's dealing with the being less than 16 technically. As far as our range for this one, now I need to think a little bit more about how do logarithms behave. A range for a logarithm generally should be everything from negative infinity to positive infinity, but kind of similar to what happened with the last question, there is kind of a top number I can actually get on the inside, and that number being 16, because if I square two numbers, again, those would come back positive, so there's no way that subtraction would actually somehow switch to addition. So the largest thing I could get on the inside is 16. So my range for this one still will go as low as possible. I can plug in any number, or technically the more negative that number becomes on the inside, the smaller that value, or the closer to 0, I guess, the inside number gets, the closer the y value of that would be negative infinity. So that's going to go down forever. But that does, again, max out at the highest value for the inside is actually the natural log of whatever 16 is, which is not really a nice, easy, perfect number. So I'm just going to go ahead and include the fact that the natural log of 16 would be technically the largest thing I could get back for this one. Because if I plugged in 0 for x and y, I would get 16 on the inside, and natural log of 16 still would be a part of this graph. So hence the bracket instead of the parenthesis. Now on to some finally calculus-based questions. So 5 and 6 essentially are asking us to do the same thing once again. So these are just evaluate what are the partial derivatives, either with respect to x or y, as denoted by the f subscript x or f subscript y. And then basically what we'll do then is just plug in the point that they provided. In this case, it's the 2, -3. So first and foremost with these questions, I just need to figure out what is the partial derivative here with respect to x. So notice again when we do partial derivatives, I'm not too worried about the x comma y, I'll just say fx. This is going to be anything that's not the letter x. I basically treat like it's just a number or a coefficient if it's attached to something. So 3x squared, that is the variable I'm dealing with. So 3x squared, that's a derivative that would be 6x just using power rule. Added with, here I've got 4xy, so this y, I just kind of need to think the 4 and the y technically are multiplying, they're just a different number or coefficient on the x. So here it would just be only the 4y that would be left because the derivative of x technically turns into 1. And then the last part, the y squared, again, we're treating that like it's a number, so that's really just like it's a constant, and the derivative of any constant would just zero out. Similarly, we can do the partial derivative with respect to y. We're doing essentially the same thing, except this time we're basing everything on the letter y. So that 3x squared, we're treating that like it's a constant, so that's going to zero out. 4xy, that's just a coefficient of 4x that's on that, so it's going to be 4x. And then minus y squared's derivative, that's going to be a 2y, because we're doing, again, with respect to y. So now at this point I just plug in the point that they've provided for us and simplify. So if I wanted to do fx of this to -3, I just put in 2 where I see x, so it's going to be 6 times 2 plus and a -3 anywhere y is, so that gives me 4 times -3. So it looks like I got 12, take away 12, which gives me 0. If I look at the fy of that same ordered pair, so function with respect to y, or this is essentially the slope in the y direction if you really wanted to describe what this is. I'm not going to plug in those same points, but now to my partial with respect to y, so 4 times 2 minus 2 times -3, so that gives me what? An 8 plus 6 due to the minus and negative, so 8 plus 6, that's going to take me up to 14. So it looks like this is kind of flat in the x direction, but definitely very steep in a positive way in the y direction for this one. So hopefully that makes sense when it comes down to it. Again, we just had to do the partial derivatives and then plug in a point. Number 6, again, just basically the same situation. This one just a little tougher just because we've got it looks like a quotient going on, so I'm going to have to remember our quotient rules. So if I maybe just throw that up on the top right corner here. Recall if we were doing the derivative, I guess this is probably not the best notation, but d over dx from earlier in the year. If I had a divided by b as what I was doing, that would be essentially do let's see, a prime times b minus a times b prime all over, and then b squared technically is like the formatting for our quotient rule. Here though, when I'm doing my partial derivatives, again, if I'm only doing with respect to x, I just treat all of the y's or any other variable like it's a constant, so maybe it won't be as crazy as maybe it looks like it might be, because I don't have to worry about the product rules that maybe I would have had to worry about if this was like an implicit function. So here, or if we were actually just trying to find what is the overall derivative, in other words. But again, this is being defined as a function xy, so that's like a different output z. So this is definitely a multivariable function, not just a single implicit function. Hopefully that's not too confusing. But anyway, let's go ahead and just jump on in. This is going to be our first thing that we'll do. We'll just do the partial with respect to x. So if I do the bottom function, staying the same, x squared times y, times the derivative of the top, again with respect to x, that's just going to give me 3 minus 0, because I'm treating the y like it's a constant again, so this is going to be 3x squared y when I put all that together, minus, now it's going to be the top, so 3x minus y, keep that grouped up since that was two terms, times now the derivative of the bottom with respect to x, so that's going to be 2x, and then the y is just treated like a coefficient, so it's also still going to be there, and then all over the bottom squared. So basically if I square the bottom, that's going to become x to the 4th and a y to the 2nd. So now I just look to see if there's any way that maybe I can simplify or make this easier to do the plug-in part next. Let's go ahead and just maybe multiply some things out, see if I get some like terms. So 3x squared y minus, if I distribute this through those two, I also have the negative to worry about at the same time. So I've got negative 6x squared y, it looks like. And then a double negative on the next one is going to switch that to addition. And then 2xy times y, that would be 2xy squared. And still all over the x to the fourth, y to the second. So simplifying that even further, it looks like I could combine my x squared y's. I can also do a little bit of factoring. I'll try and do that here as two separate steps. 3x squared y, that would be negative, because 3 take away 6 is negative 3, plus the 2x y squared over x to the fourth y squared. I can factor, it looks like, an x out from the top. I can also factor a single y out from the top, and that would leave me with a negative 3x. I guess there wouldn't be a y left on that first term anymore. And then plus 2 and only y. So it looks like those will get to reduce with this x squared and x to the fourth and y squared on the bottom, and turn into, it looks like, kind of not using my space super great here, sorry about that. So negative 3x plus 2y, still on top, that's all that was going to be left. This x will cancel one of the x's to leave me x cubed, and that y will cancel one of those y's to leave me just a single y. So now I can plug in that point negative 1, positive 1, so I'm just going to write that underneath here. This would be negative 3 times negative 1 plus 2 times positive 1 all over a negative 1 that's being cubed times a positive 1. Simplifying that, I get a positive 3 plus 2 over negative 1 times 1, so negative 1. So it looks like 5 over negative 1, so negative 5 as the final result for that one. The partial derivative with respect to y is going to be very similar steps. Hopefully this one will simplify a little bit easier, just because I don't have a power at least on the y's, so this might turn out a little bit nicer. But here it's going to be the same pattern, so derivative of the top with respect to y, that's just going to be a negative 1 minus, times the bottom, x squared y, minus, there we go, sorry, misspoke there for a second. Now it's the top function, so 3x minus y times the derivative of the bottom, which is just going to be, with respect to y, that's just going to be x squared over, and then let's see, I've got the bottom that's just going to be squared again, so x to the fourth, y to the second. So it's maybe be a little bit smarter about our factoring here maybe at the beginning. Let's see, I can take out, looks like they both have an x squared for sure. They both also have a negative, so let's just take negative x squared out. That would leave me positive y from this first term. And then let's see, if I take that negative out, that's now going to be plus this 3x minus y. So again, I've taken this x squared and this x squared and factored them out. So y, take away y, actually is going to reduce down to a 0. And the bottom still is x to the fourth y squared. Now that negative x squared here can reduce with 2 of those x's on the bottom, leaving me x squared down there. So all together, it looks like I've just got negative 3x left over on top. So it looks like I actually could factor even further. Dang. Over x squared, y squared. Reduce one more of those x's, and I get negative 3 is all by itself on top over an x times y squared. There we go. Now we finally got it simplified. So plugging in negative 1, positive 1, I got negative 3 over negative 1 times positive 1 squared. So it looks like just a negative 3 over a negative 1, which is 3. So the value of this one would be 3. Again, each of these just representing the slope in either the x direction or the y direction on this three-dimensional graph if we were to actually go through and graph it. On to questions 7 and 8. So 7 and 8 are now actually wanting us to identify the extrema or saddle points for these multivariable functions or 3D graphs. So here it does give us a little bit of extra info. It does want us to specifically answer in the end as ordered triples, so kind of just take note of that. And then also we need to make a clear label of whether it's a maximin or a saddle point. Really for saddle point, SP is going to be fine enough for me. But anyway, let's go ahead and look at what we've got here. They give us this function. In order to be able to get critical numbers, I have to get my first partials, so I think that's a good start. So if we just go with fx first, identify what its value is, I just do the partial with respect to x. So every y I'm just treating like they're numbers then. So 2x squared, I can do that derivative with power rule. That's just 4x. Y to the fourth, that's just a constant. At least with this, we're treating y like it's a number, so that's going to zero out. And then for xy, its derivative would be just 4y as the coefficient that's attached to that x. And then minus 4 at the end would zero out, just like the y to the fourth did. If I do a similar step with the fy, but now it's the partial with respect to y, 2x squared now is going to be like a constant, so that's going to zero out. Y to the fourth, I can do power rule with 4y cubed. For xy, that's going to leave me 4x as its coefficient on that y, and then minus 4 again turns into 0. So now my goal is to essentially try and figure out what are my critical points, and the way I would do that here is just set each of these equal to 0 and solve. Since both of them have an x and a y, I basically just need to use one of them, isolate a letter, so I can then substitute into the other function, whatever that value would be. So it looks like my partial with respect to x is probably the easier one to deal with. I'm going to go ahead and just subtract the 4y over, so I've got 4x is equal to negative 4y. So I could technically just replace that 4x with negative 4y right there, or I can do one extra step and just divide by 4 and get that x should equal negative y. So it looks like if I get these, or when I get these ordered pairs, that the x value is just the opposite of whatever the y value is, or vice versa. So I'm going to go ahead and just substitute in, like I kind of mentioned before, 4x is negative 4y according to what we just had over there, so let's just take advantage of that. So I get 4y cubed minus 4y after I do that substitution, and now I just should be able to solve for y with a little bit of factoring. So they both have 4, they both have a y, so I can factor that out. Y squared would be left from the first term, and then a negative 1 must be left from the second term. So now setting each part equal to 0, 4y equals 0 at 0 itself. So there's one solution. Y squared minus 1 equals 0 at a couple of numbers, both positive 1 and negative 1. So it looks like my ordered pairs, or my key points, are going to be, I've got 0, 0. Again, the x values are just the opposites. The next one, if the y is 1, its x must be negative 1. And then the last one, if its y value is negative 1, its x value must be positive 1. So there's my 3 key points. I just need to now identify what are the d values. So this is going to be utilizing the d test, which, just as a quick reminder, the d value is going to be whatever the fxx function is at that point times whatever the fyy function is at that point, and then minus whatever the fxy function is squared. And ultimately we're looking to see, does that d value come back positive, does it come back negative, or does it come back equal to 0? The only one that we really don't want to see necessarily is when it equals 0. That just is something where that test doesn't work. So I'm hoping that the d values will either be a positive number or a negative number. If it's positive, that means it will be either a max or a min. If it's negative, that's just going to be a saddle point. So that's now the second part of this question. I just need to get now the second partials, the fxx and the fxy, as well as the fyy. So let's just figure out what those things are. So fxx, let's start maybe with that one. Let's just take the second derivative of the first partial with respect to x. So fxx, if I could speak here, I got 4x will just turn into a 4, and 4y, that's just treated like a constant, so that's going to zero out. fyy, we can do that one relatively quick, hopefully. So that would be the y, or first partial with respect to y, done with respect to y again. So 4y cubed will turn into 12y squared. And 4x, just like before, that's going to be treated like it's a constant, so that turns into 0. And then fxy is the last one I would need to do. And then that would be the fx now do its derivative with respect to y. So 4x would turn into 0. 4y would just leave 4. And so it looks like I got a couple of these that are just constants. So now I just need to evaluate each of these points to find their d value. So if I plug in 0, 0 to that formula at the top, my fxx at 0, 0 is 4. My fyy at 0, 12 times 0 would stay 0. Minus, and then fxy, that's 4. 4 squared, that would be 16. So it looks like I've got 0 take away 16, which is negative 16. So we can maybe go ahead and commit to, if I go ahead and change color here at the bottom, I know at 0, 0, let's see what happens when I plug in zeros everywhere. I get -4 as that z value. I know that that's a saddle point. Because that came back negative, that's the reason I'm able to make that conclusion. So the next one is going to be something about -1, 1, whatever its z value will be, and then the next one, +1, -1, whatever its z value would be. Guess we can maybe go ahead and just evaluate each of those, maybe with a little mental math here, just plugging into the original function. So let's see, if I plug in -1, +1, I'd end up with 2 times 1 is 2, plus 1, so 3, then I've got -4, so -1, -4 more, so that's -5. And if I did the same thing with +1, -1, I think I get the same numbers as I go through. Let's see, double checking though. 2 plus 1 is 3, would in fact be -4 again, so another -5. So now I just need to figure out what are the d values. Are these going to be maxes, mins, or is it inconclusive based on this test? So let's go ahead and just plug them in. Let's see what happens. So plugging in, let's see, fxx, that's still going to stay at 4 for this one. Plug in -1, 1 to fyy. Well, fyy is 12y squared, so 1 squared is 1, times 12 would be 12. Minus, and then the fxy, that's 4 again, squared, so it looks like I've got 48. Take away 16, that would be +32. Since that came back positive, we can now make the conclusion that that point specifically, which we said was -1, 1, -5, that's going to be a minimum because the fxx is a positive value. If the fxx was a negative value, which is not possible because it's just a constant 4, it could be a max, but in this case it's a positive, so it's only got an option of being a min. So I'm going to guess it's probably going to do the same thing for this last one, but let's just double check I in fact don't get 0 for the d value. But with it being 1 and -1, I feel like we're probably going to get the same numbers. So anyway, let's try it out. So I got 4 as my fxx at that point. 12 times -1 squared, well, -1 squared is +1 times 12 is 12 again, minus, and then the fxy is 4 still. So notice again, same number, so I get 32. So this one also happens to be a minimum. So final answer here would be these three statements. The first point at 0, 0, -4 is a saddle point, -1, 1, -5 is a min, and +1, -1, -5 is also a min. All right, on to the last one. Exact same instructions, still trying to figure out what the extrema or saddle points are. So still going to need to do our first and second partials, do the d-test, and determine what we end up with as our final conclusion. So let's go ahead and jump on in. Start with our first partial with respect to x. So for this one, that's going to be derivative of x cubed is 3x squared. Negative 12x will give me negative 12. The y cubed zeroes out, the 3y zeroes out, and the 5 zeroes out. So those are the only two terms I got left that had x's. First partial with respect to y, very similar. I got x cubed will zero out. Y cubed will become 3y squared. 12x zeroes out, 3y is negative 3, and negative 5 cancels or zeroes out as well. So now I just need to find what are those critical values. So setting each of those equal to 0 will be our process. So set equal to 0, set equal to 0. First one looks like solving for this one. Getting x by itself is all I'd be able to accomplish. So instead of being like a system of equations like the last one where I had to substitute into the other, it's more just isolate and then think of all the possible pairs from one into the other. So next would be dividing 3 over, giving me 4. Square rooting, getting two answers, positive and negative 2. Similar with the next one, add 3. 3y squared equals 3, divide by 3. Y squared equals 1, and square root, and get y equals plus or minus 1. So my ordered pairs, it looks like, would be, as far as options, are 2 with positive 1. Could have a 2 with a negative 1. Or I could have my negative 2 with positive 1, or my negative 2 with negative 1. So I've got 4 critical values to test out, or critical points for this. Again, that I'll just need to figure out what is the d value of each of these. where again the formula for that will be what's fxx times what's fyy minus what's fxy squared at each point. So let's go ahead and get what are the fxx and fxy's. So fxx, if I do that down here bottom left, that would be the derivative of the x with respect to x again. So 3x squared would become 6x, negative 12 would become 0, so that's it. Fyy, that's going to be our y with respect to y again, so 3y squared, that would be 6y, minus 3 turns into 0. And then fxy, I guess I can do that right here, would give me, since there are no y's, it's just going to be 0 minus 0, so 0. So that actually is going to make the d-test a little bit easier because I'm just going to square 0, which stays 0. So now plugging these points in, I'm going to go ahead and say what each of those will turn into. So I've got x is 2 for this first one. So if I go ahead and plug 2 into fxx, I get 6 times 2 is 12. Times y of 1 into fyy, that would be 6. Minus 0 squared, and that's going to come back positive 72. Plugging in 2 with negative 1, I basically will get the same two numbers, but this time a negative 6 instead of a positive 6, minus 0 squared, so that gives me actually negative 72. Next one, plugging in negative 2 will give me a negative 12. Positive 1 with the 6y, that's going to be a positive 6, minus 0 squared again, that's going to give me a negative 72 again. And then the last one, a negative 2, gives me a negative 12. For fxx, a negative 1 gives me negative 6 for the fyy, minus 0 squared again. But 2 negatives switches it back to a positive, so positive 72. So a whole bunch of 72s or negative 72s. So now we should be able to make our conclusions. Again, all we're doing is basing everything on what's the value of that d test, or from that d formula. And then compare what is the fxx. If it's positive, it's going to be a minimum. If it's a positive d, if it's a negative d, it's a saddle point. And let's see, what's the third option? If it's a positive d but a negative fxx, that would be a max. So let's go ahead and just find what these are. The ordered triples, I'm going to save a little bit of time in the video and just say what it would turn into. But again, I would be plugging into the original function. Just whatever these ordered pairs are. So when I plugged in 2 and 1, I got negative 23. And since at 2, 1 up here, I got positive 72, that means it's either a max or a min. And because the fxx is positive 12 right here, we can go ahead and say, since that's positive, that must be a min. I don't know what just happened there. So this is a minimum. Next one, let's do just the point right under that, 2, negative 1. When I plug in those two values, I got negative 19 from the function. And that one's a negative d value, so that would just be a saddle point. Similarly, at negative 2, 1, and its z value from the original function was, let's see, negative 2, 1, that's positive 9. That's what I got there. That's another negative d value, so that's a saddle point as well. And then the very last point, we've got negative 2, negative 1, and its z is positive 13. And if I plug in, or when I plugged into that, I got positive d, but this time it was a negative fxx. That actually means it would be a max if I do my reference to that sheet. So anyway, hopefully this is all making sense, and hopefully this video has been helpful. But if you have questions, feel free to reach out, let me know, and we'll see if we can figure it out together.